All right. Well, first off, thank you very much, everybody, for giving me part of your afternoon. I appreciate it. My name is Brennan Doherty, and my role is to travel across the country, meeting with owners, engineers, design build contractors, and architects, educating them on siphonic drainage. I myself am published. I was able to help get siphonic drainage added into ASPE's design handbook. I've also helped write the code up in Ontario to get BMEC approval, where we are currently the only approved siphonic drain in Ontario. And as of last year, I was added to the ASPE 45 Design Council that makes the standards down here in the US for siphonic. Point being, I am very well versed in the topic, and you'll see very quickly, extremely passionate about it as well. Goal of today's session is to make sure you are comfortable and confident talking about siphonic drainage around a roundtable, whether it's with somebody else on the team, talking to an architect about it, or pitching it to that owner. What is siphonic drainage? In layman's terms, when you were stealing gas from dad's car back in the day, we got that hose primed with fuel. We created a siphon effect. That is exactly what we were doing, except at the roof level. The first major difference you're going to notice, a siphonic system allows us to use roughly half the diameter storm pipe. So where you're running an 8-inch gravity line, it's going to be a 4-inch siphonic. Why is that the case? Traditional gravity drainage requires 2/3 air mixing with 1/3 water in order to efficiently transport through that system. With a siphonic drain, we're actually going to introduce a baffle plate over the top, which is going to eliminate air from entering that pipework. Because we don't have that air in there, that's how we're getting that half diameter. The second major advantage with a siphonic system is the pipe runs dead level flat. There's no installed slope or pitch whatsoever. Similar to a fire protection system, the routing as well as the demand is thrown into a hydraulic balancing program that ultimately dictates what diameter that pipework needs to be. Fire protection is based off of positive pressure. Siphonic drainage is based off of negative pressure. If I'm explaining this to a high schooler, the natural height of the building creates that hole for us. The horizontal in your fittings create your energy loss. It's that at its most basic level. Our biggest issue with traditional gravity is we're dictated by pitch. We can only go so far with that pipe before entering livable space, at which point we have to have a vertical leader. And we're going to find that all throughout our design. The intent with siphonic drainage, we want to collect everything at that top roof level, routing it to one vertical, which then allows us to define where we want that civil connection to be, rather than gravity and pitch dictating it for us. Number 3, gravity drains clog. I've been to enough roofs to know this is the case. Scupper does not alleviate that situation. What about siphonic drains? In the video I'm sharing with you right now, what we did was we took 3 giant garbage cans full of wet pine needles and leaves and threw it in here to simulate a flash storm. The first thing I want you to notice, there's no dome or debris guard over that siphonic drain. What happens with gravity is what we saw in the last video, and we know to be true. The leaf and debris end up getting pulled towards that drain, collecting on the side, meaning that water level has to rise in order to overcome that leaf and debris to exit the system. So we start seeing our wet spots, our leaks, and ultimately our roof drain failures. You'll see here after less than a minute's time when this water level's gone back down, there's no more leaf or debris left on this roof. It's pulled clean through that system. We'll go over the next few slides, what's going on, why it is having that effect. Video's great, even more impactful. We have the system installed in 1,000+ Walmarts all across the US. Point here being, every single climate, we know it's tried and true, it is going to function. Outside of just that, siphonic drainage has been around in the 1980s and predominantly used over in Europe and the rest of the world for commercial work. Point of that being, It's not a secret benefit that the self-scour is that it cleans the system. This is widely known. Outside of just Walmart, number of firms within the US we've worked with, point here being, you're not a guinea pig and we're not a high school science fair project. We know what we're doing. The biggest misconception I hear though is, we need to submerge the drain in order for it to work. Logically, I understand why that makes sense. Reality is, couldn't be further from the truth. At only a quarter inch to a half inch of ponding, that system is already going to start seeing that siphonic effect. And one of the major difference, siphonic drainage follows 4 basic flow patterns. Stage 1, any light rainfall, drizzle, a majority of the events we're going to see, it's going to act as a traditional gravity system. No different. Even though that pipe is flat, water always seeks to find its own level, its own low point. Best visual for you here. If you go home today and pour your water bottle in a plastic Glad container, the water doesn't go to one side or the other. It levels out that container. Poke a hole in the bottom, the water goes to that new level. Stage 2, this is only a quarter inch to a half inch of ponding. We're going to see the system self-scour. So if there's any leaf, debris, plastic bag, it's going to get sucked clean through at this instance. Stage 3, we're trying to get there. In stage 4, we have complete submersion of the drain. It's 100% siphonic at this point. Next video I'm going to share with you shows these 4 flow patterns in the horizontal, and then we'll take a look at the vertical, which is just even more intense when it gets to that stage 4. There is increased velocity with a siphonic system. As a result, we do have additional bracing requirements. We'll cover that in today's session. Rain event ends. System's going to clear itself the same as it does with gravity. What about noise? Because I promise the architect is going to ask you about it first thing. Noise is directly related to air mixing with fluid. If we think about any full recirculating system we have within our building, that's not generating noise for us. So stage 1, equal to gravity, no different. Stage 2, it is about 5% louder than gravity with that wave pushing through. However, when we get to stage 3, it's about 5% quieter than gravity. And then stage 4, null and void of air, it's actually about 7% quieter than gravity. We did ask Charlotte Pipe about this, and their comment was cast iron over PVC with insulation being your next best friend. But the reality is, if we have somewhere with that noise concern, an auditorium, penthouse, C-suite offices in that hospital unit, with gravity, we're dictated by pitch. We have to go wherever that pipe tells us within our design. With siphonic, at least we can route that pipe out of there as fast as humanly possible, adding something to our design toolbox we do not currently have. Most importantly, though, we have a more efficient drain, creating a safer overall roof. Not only do we have reduced maintenance costs for the lifetime of that building, not having to worry about the clogging leaves, we have a drain that's going to pull that water off the roof at a much quicker pace, which means I have less standing water. So that 30-year roof, maybe the owner is getting 40 years out of. If I have an architect that is educated, well, my roof drains can cover more square footage. So we can have less on that overall roof, less penetrations. Your trade-off in that instance, to be clear, is going to be insulation pitch. If we have 1 drain versus 2 drains, that's going to take more pitch to get it there. Now that we have our basic building blocks, let's put them together and see how it applies on real-life projects. Siphonic drainage is most widely known for warehouses, big buildings, and visually we can see why. It's for a good reason. Our decision on that roof impacts more than just that plumbing scope, but looking at everything, the elimination of these vertical downspouts, not only is that material cost, that's also install labor. the elimination of this internal excavation, which is part of our scope. But on the outside, the elimination of those civils, those manholes, the trench, the pipe, the install, the rebury. I'm talking to that architect. The elimination of the site disturbance, the carbon impact on that project. But regardless of what side of the coin I'm on, if we only have to route everything to one vertical, and this is not a complex system by any means, we cut down on the calendar days, the coordination, and the potential conflict that could arise on any project. High rises are also a great example of where to use it. Instead of having our risers all over the building, civil grabs out on the outside, collect everything at that top roof level. Route it to one vertical where we can then identify our ideal civil connection. And as you can see in this example, less roof drains were able to be used. But another real life example, hospital building using 15 roof drains going to 8 different gravity risers. So a very standard design. With Siphonic, we kept these same 15 roof drain locations. Nothing was changed, but we were able to route everything to one vertical. And in this design, we only had 13 feet of siphonic pipe, at which point it reverted back to gravity and they treated it like they have every day of their life. With the major exception being, they don't have 7 other risers. They have to worry about drawing in their model, coordinating, worrying about the purchase price as well as the install for it, figuring out how I get the chase space. Where am I going to have that routing to connect to the civil? How am I going to have that civil even come meet me to the building? Route everything to one vertical. And in this scenario, we broke back to gravity so they could tie any canopies on that lower level into the same riser stack. Nothing else changed in design. High-rise example, we're going to have overflow by code as well. Point of showing this, though, we don't necessarily have to stop that siphonic action at the roof. We can take it all the way through the building, finally breaking back to gravity-sized pipe in the civil. For our overflow, we're going to discharge to a downspout nozzle, same as we're doing with gravity. Some other reasons why we might use siphonic, instead of doing the traditional gravity design where we run to a beam, we drop into the ground, excavate underground, collecting half to the front, half to the back, civil can grab it for us. Well, number one, we have the ability to eliminate that civil completely if we want. 2, maybe I'm in a mountainous region that is having problems even getting the civil to this part of the building. Okay, well, I can offer a solution for you, project team. We can route it here using this. Or maybe that architect has a giant glass facade on their building and they don't want your downpipes anywhere near there, nor do they want your overflow cow's tongues anywhere on that. Okay, well, where can I route it to? Adding something to your design toolbox we do not currently have. Last kind of major example for us, typical warehouse, it does have different roof levels, but showing us what's possible, we were able to run this system 850 feet dead level flat, no slope or pitch whatsoever. In order to achieve this with gravity, we would need 17 feet of slope or trench or building height, all of which we know we are never going to be given. Everything on one page, though. Not only is it smaller pipe, smaller fittings, coupling, hanger, insulation, anything on that PO is added to the cost savings. Number 2, flat pipe. It's going to make life easier for us, especially if we're Revit modeling. Now storm drainage has its own dedicated plane, the same as my HVAC, my electrical, my fire protection. 3, anti-clog drain, less maintenance cost for the lifetime of that building. And number 4, less pipe work, less labor. It is easier to hang a 4-inch pipe overhead than it is to hang an 8-inch pipe sloping. Leave it at that. Rules for siphonic drainage, what we want to be aware of if we are taking a look at a project. Number 1, siphonic drainage is an engineered system. It has to be stamped off by a licensed plumbing engineer. It is both IPC as well as UPC approved, and they're both asking for the same basic thing: compliance with ASPE 45, as well as ASME A112.6.9. ASPE 45 will break apart today. ASME A112.6.9 is just a performance standard. It's making sure you don't put a random piece of metal on the roof. It does have to meet certain requirements. As far as the drains go, at their base, there's really only two models. On your left, you have your typical TPO membrane roof. Membrane goes in there, clamps down. On your right, you have your stainless steel spun drain. We use this in gutter style applications and parking sumps. If you have a stadium build with a sheet metal roof, use something like that. We'll go over some advantages and why. Other application in a parking sump, if you have a parking structure, why you would do that: you can collect more drains together, so you have less verticals. It's a smaller diameter pipe, so you have less of an impact through that sidewall, again, allowing you to collect more drains in that riser. And number three, you can define where you want that discharge point to be. So if you're using any type of rainwater collection system, you could define where that was within your building rather than having gravity and pitch tell you where it needs to be. This does give you the opportunity to add lead points to your project. We also offer ADA compliant drains. It's going to install similar to a regular strainer. Ballast guard if you're doing any type of green roof, Irma style, just to make sure that pebble or whatever is going to be that substrate is not going into the drain itself. And then last kind of option we have is using that siphonic drain in a catch basin in conjunction with trench drain. We can use non-sloping trench. We offer a 4-inch depth solution. What that adds to your project is the ability to grab that water at a further distance without having the concern of that slope. Again, water is always going to seek its own low point, always find its way into that catch basin. We just have the siphonic drain in there to give you the ability for the half diameter pipe, as well as defining where you want to have that routing. This trench drain is not to be used at grade. This is in projects, generally parking structures, we see this used most. ASPE 45, what we want to be aware of if we're looking at a project. Number one, we still have to have an overflow by code. Just because your primary is that much more efficient doesn't mean you get away from an overflow. Your overflow does not have to be siphonic just because your primary was. It can still be gravity. It can still be scupper. If it is siphonic, we're going to start with a 2-inch water dam standard, the same as we're doing with gravity, no different. Rule 1B, we need to make sure every drain on the system has a minimum design of 23 gallons per minute. What that basically means is we can't have any area drains or planar drains be connected, as they just would never receive enough rainfall rate to get to that self-scouring velocity. 23 GPM does take into account your rainfall rate. So depending on where you're designing in that country, the minimum square foot is going to change. And just to give us a quick example, if we're designing near Seattle, we're going to have a larger minimum square footage. If we're in Kansas City, somewhere with a 4-inch, smaller minimum square footage to reach that 23 GPM. As far as maximum goes, throw whatever you want at it. You're not going to hit the threshold of that drain. Rule 2, if we have separate roof levels, we need to have separate siphonic systems. And the reason being, if roof B and C were connected, we might get the chance of this roof filling up, and because of wind-driven rain, this roof not filling up at the same time, so air entering the system. Not the end of the world. Couple of design options you have. If this roof is just a small roof, just drain it to the lower roof, or you're okay with it, drain it to the lower roof. You can get rid of the system completely. You will account for that square footage. Or your second option, have 2 siphonic systems. We'll cover in the next few slides how we combine them. Rule number 3, for a siphonic system, at point of discharge, we're always going to break back to gravity flow at point of discharge. And it's 2 rules to accomplish this. Number 1, increase our pipe diameter back to our IPC or UPC flow rate. And number 2, reintroduce atmosphere. Number of ways to do this. Most cost-effective If we're breaking in the horizontal outside of the building, whatever civil is feeding that manhole, have the manhole use a slotted cover instead of a solid cover. It's going to allow that atmosphere to come back so it breaks back to gravity. That requires coordination. So a majority of our projects, we see an area drain 5 feet outside of the building. At that point, it breaks back to gravity. No coordination with civil is needed whatsoever. The third option we might see, and we saw in that first example or earlier example today, is breaking in the vertical. We need a vent that's equal diameter to our siphonic discharge. And in this scenario, it just goes right back to that roof level, at which point you break back to gravity. You treat it like you have every day of your life. Anything can be combined with it at that point. If we have this scenario of two separate roof levels that are both siphonic, we can tie them into the same vertical riser, and we only need one vent pipe that will be sized accordingly. Other way I've seen this used very well, I have a warehouse client that doesn't want to put an area drain 5 feet outside of their building. So they take that siphonic action all the way to the ground. They punch that vent out the sidewall where they then hide it behind some shrubs, at which point they've gotten their maximum siphonic savings and they're achieving code approval. For the overflow, the downspout nozzle acts as our atmospheric brake, so no additional vent pipe is needed. We do recommend breaking the gravity size pipe in the vertical before it exits the sidewall. What that is allowing it to do is slow that pace of water before it exits the building. Any fittings or horizontal you can add will also create additional friction loss, slowing that pace. Rule number 4, there are additional bracing requirements. They're very easy to suffice. Number 1, it's to the effect of seismic bracing. We need to make sure we have pipe restraint 1 to 2 feet away from every change of direction. And we want to make sure that pipe is not moving longitudinally or laterally. It is rigidly braced. Number 1, we need sway bracing every 30 feet in the horizontal. Clevis hanger is generally already there. Just add the stainless steel aircraft hanger to make sure it's taut, it's not moving. 3 and 4, we're doing for gravity already anyway. Support in the horizontal, brace it in the vertical. If you are doing a cast iron install, hold right 117 is recommended, and that's just a metal fitting that goes over that casting there. If you're doing a PVC install, the glue already achieves that same effect. As far as install on the roof goes, no different than gravity. You got your bearing pan, you got your under deck clamp, you can use one, you can use both. It just depends on that roof install type. They can also flip the bearing pan, use threaded rod to create an extension if they have insulation. And picture over here, we want these drains installed in line with the roof. This is a good install to me. What I basically mean by that, we don't want them to be sumped out in a 4x4 sump. We want it in line with the roof so it can grab water in every direction. Gravity drainage promotes water to the drain based on gravity force, pushing it to the drain. Siphonic, once it gets any thin layer of water, starts pulling water towards the drain in every direction. As far as fittings go, really no different than gravity. Something that is standing out, and I'm sure you're reading, cleanouts are not required. We 100% don't want this end style cleanout, so that's going to create a potential air pocket for us. Test T is optional, and we recommend it anytime you're going underground. Not for cleaning. Recall from earlier, only a 1/4 inch to a 1/2 inch of ponding. That system's going to self-scour cleaning every time. This is just for our inspection purposes. Water fittings test, the same as you're doing with gravity, no difference. No air fitting, no performance test is required. Last kind of little hodgepodge of things we do want to be aware of. No special pipe, nothing pressurized. Cast iron Schedule 40 PVC is what we see on a majority of our projects. If you're doing cast iron, you're only required 2-band no-hub couplings. If you are using eccentric or concentric reducers, both are approved. So whatever you have in that project is going to work. Something that is going to stand out, in the vertical, we are only allowed to restrict pipe in the direction of flow. So we're going to go from a 4-inch down to a 3-inch. The logic is that smaller diameter pipe allows that system to fill up faster so we can get to that siphonic mode quicker. But most importantly, any system out there should have a calculation report so we know there's no chance of cavitation. We do have a safe system. The reason we're able to do that is the same reason we're able to not install cleanouts, is because it's being submitted as an engineered system. Last one for us here, and we'll go over exactly how we're handling it. If that design is changing more than 8 inches, we need to update the model. I would say this is probably one of the reasons Siphonic isn't bigger, but the reality is, with technology where we're at today, this is a moot point. This is very easy to handle. How do we work together? How does MyFab support you? What we're doing differently than anybody else is we have a design assist team in Chicago. And very basically, what we need is to understand the routing that pipework is taking, both vertically as well as horizontally. That can be a Revit model, that can be blueprints with elevation. As long as we have something to mention, we can help you. What our team does is they input everything into our balancing program. Generally, the roof drains are not the same GPMs, so they're trying to figure out what diameter all this pipework needs to be. So when there is a rain event, all those tailpipes are filling up at the same time. Those drains are all entering siphonic mode at the same instance. Once we get a pass, we know we're fully compliant with the ASPE 45 standard. Our team provides back a calculation report so you can see at every single point in that system what the major metrics are. Upon request, we can generate a bill of material so you can do a quick cost exercise. Bracing is not included on there, but it's going to help you get close to your mark. But most importantly, we create the install blueprints. So no extra labor is needed on your end, and that system can be installed as it was designed. Part of generating these, my team creates a Revit model. So we provide back a Revit model. All of this is free of charge. We have it built in the cost of the drain. But part of any ISO set is also our install blueprint guidelines. And these are the rules we went over here in our session today. That way, somebody can't claim ignorance. They have every ability to educate themselves the same as you did. Above and beyond that, we also have a full written CSI spec. This is a master spec that's open. Here's how, here's why. If we're doing any government work, school work, we can't sole spec anything. But with Siphonic, you can't just take this design and throw the cheapest drain on there. Whatever design it was, it needs to be that manufacturer's drain with those metrics. No engineer in their right mind is going to design 3 different projects, but we do have to have one designed out so we can cost it out. So MyFab is listed as master spec, but it reads Mr. and Mrs. Contractor. You can use anybody you want, but at that point, you're taking ownership, you're paying for a new engineering stamp, and you're still following the CSI spec. You don't get to make up your own rules. Written within the CSI spec is a contractor pre-install call. I hold this myself personally anytime we get a PO, and I will not release the PO until we have this. So regardless of any spec, we are doing this every time. Similar to those on the call, contractors have heard of it. They haven't got a chance to do a lot of installs. What is Siphonic? Are you aware of the bracing? Are you seeing the air brake? But most importantly, how do you handle changes if and when they do arise? Contractor has the install blueprints through that chain of communication as well as the bidding process. They identify what area has changed as well as what that new measurement is and sends it into our team. Our team takes it, we update the model. If it's just removing pipe, they make that change, email back the contractor, the day goes on. If removing that bit of pipe would require this 3-inch diameter to now be 2-inch diameter pipe, they email back the engineer record, copying that contractor. Engineer record, this change has been requested. It would also require this. Do you approve? That way the engineer has the data to make an informed decision. Don't get me wrong, contractor still has to write the RFI because somebody has to get paid for the change. but we're not playing that game of telephone. Everybody's in the loop. We're there to make the change. Any new projects, we're about a 3 to 5 day turnaround. Anything live in field is 24 hours. That's going to get priority every time. That's been our stance since day one. Last section for us. I want to beat up gravity one last time and then we'll let it be. Depending on where you are designing a project in the US, it's generally going to fall under IPC or UPC code. If we are designing a building in a UPC territory, we size using our flow charts. And it's as simple as a 3-inch rainfall rate, 10,000 square foot roof, tells us we need a 6-inch roof drain in order to meet that code requirement. If we're sizing an IPC territory, we size based off of GPM flow. That is nothing more than math. And here's your factor on the left. You can see the equation played out here. Same 10,000 square foot roof at a 3-inch rainfall rate. The numbers tell us we need 314 gallons per minute in order to be code effective. Now, in order to compare these two, we need to have a drain. I'm going to take this 6-inch cast iron gravity drain from this ASPE study. So what this shows us is at given levels of ponding depth on the roof, what the GPM discharge through the drain is. If we're sizing that 10,000 square foot roof in a UPC territory, we only need one 6-inch roof drain. Simple as that, slap it on there, we've met the code requirement. If we're sizing that same roof in an IPC territory, we do take a look at performance, and I'm not hitting it with just one of these 6-inch drains. So to meet the IPC requirement, I need 2 6-inch drains. Both are approved. I have a greater point I want to make, and it's this. With gravity drainage, the more ponding we have on the roof, the more gravity force we have pushing down. That should be directly correlated to the GPM flow through the drain. However, we notice as we go from 5-inch ponding to 6, we actually have a drop in GPM performance, contrary to popular logic. Any idea why that might be happening? It goes back to the first point of our conversation today, and that is gravity drainage requires 2/3 air mixing with 1/3 water in order to efficiently transport through that system. What happens with the gravity system is as that water level rises, the weir collapses in on itself. And when I say weir, think about when you pull the plug from the bathtub and we have that tornado, but at a larger level. With gravity, once that collapses and there's no longer any air getting into that drain, it starts becoming inefficient. Don't get me wrong, siphonic will eventually plateau off. However, as we've learned today, with siphonic, it's anti-clog, so we have less maintenance costs. It's more efficient, so we should have less ponding on that roof. It's half diameter pipe, so smaller pipe. It runs dead level flat, giving us increased design flexibility. We can go ahead and have less vertical leaders all throughout our design. Less vertical leaders means less chase space I need. Less vertical means less routing, less civil connections. Less civil connections, less civil coming to the building, less civil pipe work, less slope, less dirt movement, less carbon impact, less site disturbance. See where I'm going with it. My final parting question: had you known about siphonic drainage in the past, are there any projects this would have made life easier on?